in Unit 1, more specifically, more on the measurement side, being as that we were finished off and talked about and did one calculation of density. Let's continue that. So, what is the volume of 65 grams of liquid ethanol? Again, making sure we have all those little steps by step by step by step. And some people are like, this is taking forever. Why don't you just go faster? Sorry. Mass is equal to 65 grams. Volume, I don't know what that is. So what does that mean? Because I also don't have a density. But, oh wait, it's a tabulated value, which means I can look it up. And when I look it up, I remember that it is 0.79 grams per milliliter. Also, density is equal to mass divided by volume. Now, we put what we know in here, and that is 0.79 grams per milliliter is equal to 65 grams divided by volume. Well, some of us might know what to do here. Some of us might not know what to do here. We're going to take it a little bit more methodical than maybe some would care to. But again, I'm okay with that. I'd rather be more methodical than less at the beginning. Make sure everybody's on the same page. I'm going to multiply both sides by volume, or V. By doing so, there becomes now a debate on whether or not they say that these V's cancel out or they just become a ratio of 1. Doesn't matter. Technically, we're both correct. So now we have V times 0.79 grams per milliliter is equal to 65 grams. To get V by itself, I need to divide both sides by 0.79. And again, philosophically, yes, that just technically equals 1, but we'll just say they cancel out. Leaving me with full volume equaling 65 grams divided by 0.79. And now I also need to evaluate my answer. And should my answer be bigger or should my answer be smaller? Should be bigger because I'm dividing by a really small number. Less than 1, especially with those less than 1s. My volume then becomes 82.27. Let's say, what, 2 significant digits is what I got. Oh, 3 there, but 2 significant digits there. I think we can go 82.3 milliliters. with that. Which isn't too bad. Number's bigger because if I divided, and here's always can check yourself before you really wreck yourself. Take 65 divided by 82. You should get the same answer as your tabulated value, right? It's one way to check yourself before you wreck yourself. And then my favorite one, problems like this. What is the mass of a gram in grams of a cube of gold? Got a little bling bling. If the length is 2 centimeters. And that becomes the question. Everyone looks at that and goes one direction with it, not the band. Okay? You're like, oh, how do I do this? There you go. Peterson has a sixth sense of humor here. That's what I'm looking for. Density, it was like 19.8, I think. I don't have a volume either. And you're thinking to yourself, I'm pretty sure in algebra you need at least 2 knowns and 1 unknown before you can solve the problem. And we would say, that is correct. You need to have that. But there's something very, very important given to us. One word that helps us out. Do we know what word that is? Mr. Hain, do you know what word it is? Blank. No. It's cube. Let's think about what a cube might look like within my drawing. My art classes stopped after 7th grade, not because I was awesome. It's because the art teacher said never come back. I like to tell myself it was because I was awesome, but I know better. If I drew my cube out perfectly, each one of those sides should be what? Right? Every one should be 2 centimeters. Well, how do you find the volume of a cube? Length times width times height. And then you get down to 2 times 2 times 2, which then gives me a volume of 8. Everyone seems so eager to answer questions. 8 centimeters cubed. Now I have everything I need. And why do I like this problem? Because you have to find something to find something. You got to show me that you know how to find something simple just to find something else simple. It's how we can complicate a problem and it don't even have to really work at it that hard. because density is still is equal to mass divided by volume. $19.8. Again, I might be wrong on that, but I think I'm really close. Now, some of us will look at this and say, well, at least I don't have to do that crazy weird thing with the multiply one thing and then divide by another thing just to figure it out. Here, I just need to multiply both sides by 8 centimeters cubed. So that they either A, cancel out, or B, ratio to 1. I'm just going to say cancel out because that's what I like. That's what I was taught. Yes, I understand the differences there. Multiplying by that. I then need to take that 8 times 19.8. And I get a mass of 158.4 grams of gold. Boom. Now, the device that you use for making measurements is going to be different in their accuracy. Different things have different levels. Okay? Some of them have an inherent amount of error added to them, just generally speaking. A graduated cylinder, graduated because it has lines, okay? You would be considered ungraduated, not because you don't have lines. You might, I don't know how much stress or stuff you have. It's just that you haven't graduated high school, so you'd be ungraduated. You'd be a graduated cylinder without lines, which is not a graduated cylinder. It's an ungraduated cylinder. Now, which one is best ones to use? Well, obviously syringes or pipettes would be your best. Graduated cylinders will work. They're just not always the best. A syringe is probably going to be small amounts. And a burette is something that we'll use eventually in the second half of this class. But graduated cylinders are going to be something that we're going to use very frequently. And well, you've already used them. We will be using a pipette tomorrow with a pipette bulb, because you are not to pipette by mouth, even though a lot of you suck things out with the straw. It's pipetting by mouth. And we will also not use a volumetric flask. Volumetric flasks are really nice. Usually have a high amount of degree of accuracy with those. Pipettes are better than graduated cylinders. Graduated cylinders are at least best thing to do instead of, say, like a beaker or something else. We'll do a lab that will verify that, but we'll do a lab tomorrow on density first. So, there is always going to be a certain amount of error in your measurements. Even though we don't say human error, because that will remove 10 points from your lab. I think. Maybe it's 5. I think it's 10. Okay? But usually it's an equipment error. When we say human error, it's not that, yes, to err is to be human, and you have certain discrepancies when you make measurements. Many of you are bad at measuring. It's nothing personal, okay? You're just bad at it. You're not as practiced. That's just how it goes, okay? Some of you have good practices. It's the careful. We'll talk about that later. there's always going to be a certain amount of error. Graduated cylinders are going to be plus or minus probably 2%. That's not awesome. Your pipettes are plus or minus 0.2 or 0.5%. That's much better. Okay? Because a percentage, 2% can be 2 milliliters plus or minus. So when you say 100, it could be 102 or 98. 0.5 or 2.2%, then you're looking at it saying, well, maybe it's 100.02. Now you're like, oh, that's nice. Okay? That's where you get a little bit in there, and that's why you have to know. Our science department has scales or balances that measure plus or minus 0.1 grams. So you are limited in the mass of just that inherently. The scale is a limit factor. Getting scales that went farther out, it costs money. And according to Biggie Smalls, more money, more problems. And trust me, you have more problems when you have a higher end scale, because your level of accuracy is much higher. So we don't buy those. Try not to. Again, chemistry is Peterson making your lives easier. Okay, I'm taking away those problems. Okay. Can't take away all, just some of the measuring ones. So there's a certain level of uncertainty. So when it says that it's 22 grams, like last week when we were doing that, you wanted 2 grams of your Epsom salt. Well, even when it read 2 grams, that's not saying that it's exactly 2 grams. Even if it's 2.0, it actually could be 1.9 or 2.1. Don't know. That's why when someone would measure out 2.1, I would say, close enough. Why? Because it could be 2.0. But it could also be 2.2. Now 2.2, try to take off a little bit. But with you, if you're in that plus or minus range, usually you're good. And that's okay. Now, 2 terms that very greatly and widely get confused with themselves. So much so that I've even had to lecture my wife on the differences between them. And if you question whether or not I did it, you obviously don't know what kind of a person I am. Yes, I did lecture her on that. She said one and I meant the other, and I was like, I don't think you got that right. And then I got the wonderful, you know what I mean. You're right, I do, because I work with teenagers and they get it wrong all the time. So, precision. How close individual measurements are. Accuracy. How close results are to the true value. I like this way of writing it is accuracy actual. You get a word association. Right? How close are you to the actual number? Precision, things are really close. Okay? Now, I use this example because some people have done it. If you've ever shot a bow and arrow, everyone wants to shoot a bow and arrow, it's like the same thing as throwing darts, right? You want to be as close to the center as you can. Except for when you're throwing darts, the triple 20 is actually the highest one, and therefore you actually wouldn't be aiming for bullseye. But for the sake of science, we always want to aim for the bullseye because that's the actual. Okay? You're sighting in your bow or a gun. There's a lot that can be said from these terms. If you hit the target dead center, That has good accuracy. Now, if it's the first time you're shooting with that gun, your accuracy might not be all that great. Why? Because there's a little bit of the how does the gun shoot? Or how does the bow come off? And it's the same thing when you're using sights on a bow. What you want to try and get is B when you're sighting it at something like that. Some people look at me like, what do you mean you want B? You want a close grouping. Yes, it says, hey, guess what, you're wrong. But you're at least consistently wrong. That can be fixed. A couple dials here, a couple dials there. Your sights can be fixed. Then you shoot again and see and hope that your precision still stays true. And then that maybe your accuracy is then helped out. If you're at C, you're all over the place. We can't help that. Okay? We can't help you if you're all over the place, abstract random. It's like, we need to at least get you consistently wrong before we can at least figure out what you're doing wrong. Like, but yeah, I'm wrong. Yes, you're right. You might be wrong, but at least I can figure out what you're doing wrong if you're consistently wrong. Now, what happens every now and then you get these, and it's always hilarious, or at least I find it hilarious, and it's frustrating for some people. Draw another target there, right? What happens when you have people who shoot there, and shoot there? Or maybe they make measurements that hit those marks, and when you average them out, where do they end up? Pretty darn close to the middle. We would say their precision is poor, but their accuracy is good. And those people, we say, how did you do that? And they go, I don't know. Because they're just kind of guessing on where they're going with stuff, and they just luck out every now and then. Most of the people don't like that in the lab. Because they're like, but you have really bad practices. Yes, they might. However, that happens every now and then. Okay? Accuracy, actual. Precision, close. We can fix precision. It's usually a practice. There is an equation that goes along with that as well. It's a very big equation. Accepted value is sometimes one that we would have, or the actual value, but a lot of better term is actually saying the accepted value. And it's better to say accepted value because is it really the actual? Or at least this is just what we're going to go with as the acceptable answer. Usually the tabulated values, say for, I don't know, density, are considered to be the accepted values. In your lab over the next 2 days, because we're A day and B day people, we have our first calculations will be in our lab book. So make note of that. We will have our first calculations in our lab book. You're going to be calculating density. So you'll have to put the density equation in your lab book. Also, you're going to be having to ask some and do some percent error calculations, which means you will need to put in this equation into your lab book. Now, these lines here, some of you may or may not recognize them. Absolute values, meaning that the answer out of those can never be negative, always positive. Okay? Might seem simple, elementary, but never. The experimental is what you do in the lab. Okay? Hint, hint, you're going to be calculating and doing some, finding the density of some items. That is going to be your experimental value. The accepted ones are usually tabulated. A lot of times students worry about, oh my gosh, my percent error is terrible, it's astronomical. That's okay. I'm not grading on your percent error at this time. You're still learning how to make good measurements. Okay? At some point, we will grade you on your percent error. Okay? It is a thing. There is also another equation that we didn't mention originally, and that is range. Largest minus the smallest. You have a large range, that's not good. Small range, good. That means all your numbers are really close to each other. So that's another equation or another thing that you can do. There are countless others as well. Averages, standard deviations, and all that. Average is easy to do. Standard deviation, probably not worth our time at this moment. So it's there.